Science observations related to Jupiter Reimagined. First, please note there's a difference between an observation and an interpretation of an observation. So the legacy standard model of Jupiter interprets observations such that Jupiter is all gas, primarily hydrogen and helium, in different states, gas, liquid, and metal. And Mass Vortex Theory interprets observations such that Jupiter has two cores and a regular rocky body. The rocky body is topped by a deep ocean, atmosphere, and ice shell. So we'll be looking at the science observations that are referenced in the video Jupiter Reimagined. First up is the Hubble images. So these Hubble images are a form of observation, and the images are in ultraviolet and visible light. Hubble has several instruments on board, and Judy Schmidt used the Wide Field Camera 3, and there's different channels. She used the UV and visible light channel, which has records radiation in the range of 200 to 1,000 nanometers. And these are the filters that she used for both images in red, green, and blue. She assigned values to those. So in Saturn, we know from the Cassini probe that the C ring is composed of ice. So there's a little bit of space in between some of those particles, but we know that that color now is gives us a calibration that it is the color of ice, brown. Then in this picture we see that the brown, where there isn't space between the different particles, it shows ice in the polar regions of Jupiter. The same filters were used for this image as the previous image, and this is an indication that they're of the ice shell visually. The moment of inertia factor. So Jupiter's moment of inertia factor is an observation, and it gets interpreted for the internal distribution of mass. So this is the actual formula for moment of inertia factor. And the moment of inertia around the axis of rotation, the mass, and the radius are all observed values. The values for moment of inertia go from 0.4, which means that the mass is distributed uniformly from the center radially to the surface, and very close to 0 means that all the mass is at the center point. For Earth, a planet we know, the volume of the inner 50% of the radius has much more mass density than the volume of the outer 50%. You can see the inner core and outer core goes from like 13 grams per centimeter cubed to 10, and then the mantle is 3.3 to 5.7, and the crust, which is very thin and hardly contributes at all, neither does the ocean, and that's what it looks like for a moment of inertia factor 0.3308. So the currently favored model for the interior of Jupiter is given by this figure in David Stevenson's article on the Jupiter's interior as revealed by Juno. And we see here that this orange sort of layer outside is the outer atmosphere. And then there's a weakly conducting layer and highly conducting layer that are called the molecular hydrogen shell. And then there's a big metallic mantle, and then a core where there is heavy elements, unidentified heavy elements with hydrogen diluting those heavy elements. And I did some calculations based on the ranges of what the densities are of each of these layers, and came to it's about like this. The 30%, 45, 20 are the three layers, and they go from 11, like around 11.6 to 0.1, 0.001, even less. I wanted to show this is has to do with the calculations, and if you make the 11.6 higher, you're going to have too much mass. If you make this 3.5 lower, you get quite a bit lower mass. So these figures work out to calculate so that they form the calculated mean planet density, as well as accounting for 100% of the mass. Now, in the Mass Vortex Theory version of Jupiter's distribution of mass, almost all the mass is distributed between the bottom of the ocean and the center point of the planet. And I believe this is more in keeping with having a moment of inertia factor of 0.276. These are the mass densities that we're talking about. It's called a faux core because there's really two cores. So for this image, we're merging them together for one. And yes, almost all of the mass is below the ocean, and then the outer parts of the planet have very low mass density. But you can see that the atmosphere is a very wide layer, so it would contain a fair amount of mass. Okay, Rayleigh scattering. Rayleigh scattering of ultraviolet light in the upper latitudes, either 45 degrees or negative 45 degrees to positive 90 at the pole, or negative 90 at the South Pole. The Rayleigh scattering is absent. UV light is missing in the wavelength range that ice absorbs. Thus, missing UV light scattering is an indication of the presence of ice, enough ice to absorb all of the UV light from the sun. So what is Rayleigh scattering? Rayleigh scattering happens when the electromagnetic radiation is scattered by particles much smaller than the wavelength of the light. How much smaller? Typically less than 1/10 of the wavelength. This picture is denoting some of that scattering, and it's especially true for the violet and blue spectrum of electromagnetic radiation, whereas the other light pretty much flows through and doesn't scatter, as well, not nearly as much anyway. Ultraviolet, the light that I examined in Juno, was in the wavelength range from 120 nanometers to 180 nanometers. And according to scientists, the outer gases are supposed to be hydrogen like 86.5% by volume and helium 13.5% by volume. The active diameter for hydrogen, and it's usually in the form of H2, molecular hydrogen, 2.89 times 10 to the negative 10 meters, and helium 2.6 times 10 to the negative 10 meters, whereas the wavelength of the UV light is in the 10 to the negative 11 range, 1.2 and 1.8. So UV light is expected to have Rayleigh scattering at all latitudes, since the wavelength of the UV light is larger than the atoms in the outer gases. And H2 and helium, hydrogen and helium, are supposed to be present in the highest abundance over all the surface. So we'd expect scattering that would be pretty constant across the board. This is 120 nanometers here, and this is 220 nanometers here. But what was actually observed using the ultraviolet instrument on Juno was more like these two charts. This was on a particular perijove, but this is very typical of what was seen, so that there's really no ultraviolet light collected until you start getting a little bit at 180, and then it really starts to ramp up at 200. Well, observations from Juno showing no scattering in the wavelengths of 120 to 180 nanometers. If an ice shell was present under the outer gases, the observed lack of UV from 120 nanometers to 180 is what would be expected. This image from the Juno cam shows blue atmosphere under the thin outer gases and ice shell. Thus, the visible and UV light are transmitted through the ice shell to cause Rayleigh scattering in Jupiter's true atmosphere, which is beneath the ice shell. So 4, gravity harmonics. The actual observation is that Juno provided the values for the gravity harmonics. They're indicated by J with indexing subscript. And the gravity harmonics from work done by Tristan Guillot and his team finds that the outer gases at the equator go to a depth of 3,000 kilometers. This is a figure from the paper by Tristan Guillot and his team. And they did use existing models, the trusted models with hydrogen and helium for the integrals and so forth. But it shows this is like, you can see 2,000 here, and this goes up. This is 5,000, 2,000, and the peak is between that. So this is the constraint on the depth. The depth of Jupiter's zonal flow obtained by from interior models, and Juno's even gravitational harmonics. So that means that this orange layer here and this layer over here, that's sort of a tan color, these are the outer gas layers as seen in both models. And pretty much in both models, we're distributing the layers evenly over the surface of the planet, even though there is a bulge at the equator. So from my point of view, the gases are, say, 3,500 kilometers at the equator and get very much thinner at the poles and the polar region. So another observation is the gravity map that came out of data from Juno. And East et al. With team made a gravity map. And another team, this is the gravity map. And the Mass Vortex Theory interprets the gravity map to show us that there are two cores in Jupiter's interior. So we have this map is in the background, and then I applied the rose-colored lines on top to indicate the peak of the lower core, the peak of the upper core, and the middle where the overlap happens. So that's the Mass Vortex Theory interpretation of the observation made based on Juno's data. Magnetism maps are also an observation based on Juno data. And there were two different teams that created maps of the magnetic fields on the surface of Jupiter. First up is Moore, K.M. Moore. She and her team produced this map. And we see that this red region is not right at the pole. And this blue region is about, at the equator. This is another map by the same team. You can pause and read information. This comes from the article that was done by the team. And here we get polar views to look at how, like, this is the North Pole, and there's a red, a fairly significant red region here close to the pole, but this one is off to the side, and so is this big one. And this is the South Pole with all blue, which is negative Gauss. This is another map done by the same team. So now looking at mass vortex theory, planet formation model, and this comes from many observations, not just Jupiter, not just Saturn, but many observations, and fitting the data, fitting the information together, and looking at how everything can fit together. Mass vortex theory sees that part of a nebula responds to a singularity when a singularity becomes present, and this turns into a vortex and then a disk. The vortex breaks up the gases from the nebula into a geometric spiral that ends at the singularity. Two clumps of iron close together when spinning out of the vortex attract each other in the lane where Jupiter forms. Two clumps of iron far apart, however, form two separate planets in the lane between Mars and Jupiter. Explanation about these two planets, which I call Elo and Smithereens, and what happened to them, is outside the scope of this presentation. This image attempts to show what the arrangement of the iron-rich gas in the region where our solar system formed. It is on a logarithmic scale, and the darker the cloud, the more rich it is in iron. So the parent cloud of our solar system had gas in arrangement somewhat like this. And you can see where there is iron close together in one path from the geometric spiral that is made when the vortex gets started. And then in the next path, the iron clouds are spaced out. So this, in a more sort of close-up, the two clouds here get split to form the two cores of Jupiter, and then the planet Elo forms here, and later Smithereens forms and crashes into Elo. In physics, when we know that the magnetic fields are going in the same direction, that there is an attractive force, and you can see it here in this diagram also. This is what is behind the two cores of Jupiter, where they come out of the vortex and they're spinning in the same direction, and then they attract each other. This presentation has covered mass vortex theory's interpretations of observations. And here is a figure that puts together observations in theory to show Jupiter's interior. We have two cores that are not aligned. The northern core causes mantle and crust to rise above the ocean, possibly. It's a fairly deep ocean, hard to know. Light enters from about 45 degrees north to 90 degrees north. And light enters in the lower southern latitudes also. The crust is much thicker as a percent of Jupiter's radius because it exited the vortex very early. And the longer a planet is in the parent vortex, the more it's accreted atom mist around the iron cloud gets scrubbed. So Earth's late exit caused very little accreted atom mist. And then the heat from the two cores made larger initial steam cooling. So it made for a thicker ice layer. and a large distance from the surface of the planet before the steam cooled to ice. This image was taken with ESO's Very Large Telescope. I think it does a nice job of showing the ice shell underneath the gases. Thank you for your attention for this presentation. I hope that it clears up my claim that the Jupiter Reimagined does fit with the observations that have been made about Jupiter, even though it is very different from the accepted, what I would like to call legacy model of Jupiter.